exploring space, it's inherently risky, right? I mean, pushing those boundaries. And history, oh boy, it has some stark reminders for us.
Yeah, for sure.
So today, we're going to dive deep, really deep, into what could be, well, what many consider the biggest, like the absolute biggest engineering disaster in space.
It's a tough one to define biggest, but we'll get into that.
Exactly. You've brought some really fascinating material to the table, and our mission here is to, pull out those crucial insights, those takeaways from some really significant failures. We're talking Apollo 1, Challenger, Columbia.
Oh, and let's not forget those Soyuz missions, Soyuz 1, Soyuz 11,
Mhm.
and, well, not in space, the Netherlands catastrophe on the ground that can't be ignored.
Right, right. So we're going to break down those engineering breakdowns, those critical moments, and really see what lessons we can learn, what we can take away from all of this. So let's start at the beginning. Apollo 1. This was supposed to be the first crewed Apollo mission, testing the Block I command and service module, basically the heart of the Apollo spacecraft, getting it ready for Earth orbit. But it never even made it off the ground.
Tragic, absolutely tragic. A fire erupted during a ground test, a plugs out test, they call it, running on internal power, fatal.
And the crazy thing is, no propellants were even loaded. But still, a whole series of, I guess you could say, design choices, they ended up creating this, well, a death trap.
Yeah. I mean, the pure oxygen atmosphere, that was a big one. Higher pressure than what we normally experience. NASA, their thinking was, okay, let's simulate space. Makes sense, right? But on the ground, down here on Earth, well, that just created an incredibly flammable environment.
Like a tinderbox waiting to go up.
Exactly. And to make matters worse, the capsule itself, it was full of combustible materials, nylon, foam padding, even Velcro. All of that in that oxygen-rich environment, it was just fuel waiting for a spark. And this, it highlights something crucial, a really vital point. When we're designing for space, we've got to test those materials in the exact environment they'll be used in.
So important. So then, what actually caused the spark? What ignited it all?
Well, the most likely culprit seems to be a damaged wire near a coolant line. And the potential reaction between that coolant and the wire in that pure oxygen, oh, it was just a disaster waiting to happen.
Like a ticking time bomb.
And then you add in the hatch, inward opening hatch. As the internal pressure increased, that hatch sealed tighter and tighter. 5 minutes, 5 precious minutes, that's how long it took to open. Escape? Impossible.
The fire spread so fast, unbelievably fast. And those 3 astronauts, Grissom, White, Chaffee, they lost their lives to carbon monoxide poisoning. The impact of this, the fallout, it was massive.
Oh, yeah. The Block I design, scrapped, completely replaced by the Block 2, fire-resistant materials, outward opening hatch, all of that. They completely overhauled those safety protocols. Everything was reevaluated.
Right, right. A turning point, really. So, okay, let's move on to 1986, the Space Shuttle Challenger. This mission, I mean, it was in the news everywhere, carrying the first teacher in space, Krista McAuliffe, but it ended in that horrible catastrophe just moments after launch.
73 seconds, that's all it took. An explosion ripped through the shuttle and the cause. It all came down to the failure of those O-ring seals in the joints of the right solid rocket booster. And the thing is, engineers had raised concerns about these seals, especially in cold temperatures.
Yeah, I remember hearing about that. So this design flaw, it essentially made the O-ring stiff, right?
Right.
Unable to seal properly when it was cold. And of course, launch day, incredibly cold, unusually cold.
Absolutely. And the decision to launch, even with those warnings from Morton Thiokol engineers, that really highlights a dangerous mindset. Prioritizing the schedule, the timeline, over safety. A chilling example of what can happen.
It really is. So during the ascent, this joint rotations, they call it, that further compromised the already weakened O-rings, didn't it?
Right, and there were early signs, a puff of smoke right at the start, but then this flame, it just burned through the external tank, and that was it. The shuttle, it just disintegrated, 7 astronauts gone, and the entire program grounded.
The Rogers Commission, they investigated and they confirmed the O-ring failure. But what's even more important, what they uncovered, were those deep-seated organizational issues at NASA, a culture that, in many ways, contributed to the disaster.
Yeah, a culture that needed a serious shakeup. So then we come to 2003, the Space Shuttle Columbia. This one, a 16-day science mission, a successful mission until re-entry, a tragic end to a successful flight.
Absolutely. And the immediate cause, it was that piece of foam insulation. Broke off from the external tank during launch and hit the left wing. It seemed like a minor thing at the time.
You would think so, right? But that foam strike, it damaged the thermal protection system on the wing's leading edge. And the real issue here, a concept called normalization of deviance. See, foam strikes had happened before on other missions, but the risk, it was underestimated.
Complacency almost.
Yeah, I guess you could say that. So during re-entry, those superheated gases, they just penetrated that damaged area, and the wing, it just couldn't take it. Structural failure.
And what's really striking, the engineers, some of them, they actually observed the foam strike. They requested further investigation. They wanted more images, but they were rebuffed. The Columbia Accident Investigation Board, they were very critical of NASA's organizational culture. They saw echoes of Challenger in that.
Right. The same systemic issues cropping up again, 7 more lives lost. The shuttle program grounded again. And the CAIB, their recommendations, they really pushed for change. Ultimately, they played a role in the retirement of the entire space shuttle program.
A huge turning point for NASA, for sure. Okay, so let's shift gears a bit. Let's talk about the Soviet space program. Soyuz 1, back in 1967. This marked the first crewed flight of the Soyuz spacecraft, and really shows how even something that seems like a minor system failure, well, it can be absolutely deadly in space.
Vladimir Komarov, he was the cosmonaut on board. He ran into technical difficulties almost immediately. In orbit, a solar panel failed, among other things. But the fatal issue, what brought him down, was the main parachute. It just wouldn't deploy during re-entry.
A parachute failure, that's terrifying.
Absolutely. And there were a few possible causes. Maybe a manufacturing defect, maybe an issue with the deployment force itself. But then the backup parachute, it failed too. It got tangled. And the capsule, well, it just slammed into the ground at high speed. The first in-flight fatality in spaceflight history.
Really puts into perspective the absolute importance of redundancy of backup systems.
For sure. This tragedy, it led to an 18-month halt in Soyuz flights. They completely redesigned the parachute system, and it also revealed the immense pressure the Soviets were under to achieve those space milestones.
A lot riding on those missions. Okay, so then there's Soyuz 11, 1971. This was the only crewed mission to Salyut 1, the first space station. And they set a record, spending 22 days in space. But their return, it was another tragedy.
A long mission and then a tragic end. They came back to Earth, re-entry, landing, all of it seemed normal. But when they opened the hatch, the crew, Dobrovolsky, Volkov, Patsiev, they were dead.
How? They landed safely. What happened?
It turned out to be a breathing ventilation valve. It opened prematurely, way too early at high altitude, probably because of the shock from the module separation.
A tiny valve causing such a huge disaster.
It's incredible, right? So the capsule, it depressurized rapidly. And the crew, they weren't wearing pressure suits at the time. Asphyxiation, decompression sickness, that's what got them. The only humans to actually die in space itself.
It's hard to fathom.
Yeah. Another suspension of manned flights. Another redesign of the Soyuz. This time, they made pressure suits mandatory during launch and re-entry. They even had to reduce the crew size to make room for the suits. A high price to pay for that lesson.
Absolutely. Okay, so last one, and it's a bit different. The Nedelin catastrophe, 1960. This one happened on the ground at the Baikonur Cosmodrome. A missile explosion. But even though it wasn't in space, it had a huge impact on the Soviet space program.
Yeah, it was a major setback. They were testing an ICBM, the R-16, and during the test, the second stage engine, it just ignited accidentally. And the propellants they were using, hypergolic propellants, extremely toxic, self-igniting, a huge explosion.
So a combination of technical issues and, I guess, some bad decisions.
Well, there was political pressure. They wanted to launch by a specific anniversary, and Marshal Nedelin, he was in charge, and he insisted on going ahead with the test, even though there were technical problems like a squib explosion, melted wiring. And he was even on the launch pad himself, along with other personnel who weren't essential, against safety advice.
Wow. So a lot of factors came together to create this perfect storm.
Yeah, and the result, devastating. They estimate between 74 and 126 people were killed, including Nedelin himself. The deadliest launch pad accident in history.
That's just unimaginable.
It was. The Soviets, they kept it secret for decades. They even fabricated a story about a plane crash. It wasn't officially acknowledged until 1989. This event, it really speaks to the dangers of letting political pressure override safety protocols and the impact of secrecy, how it can hinder learning from mistakes.
Right. So we've talked about all these different events, the engineering failures, the loss of life, the long-term consequences. Trying to define which one was the biggest disaster, it's really tough. The Nedelin catastrophe, that had the highest death toll by far.
No question about that. But it was on the ground, and the context, it was different.
True. But when you look at, say, the Challenger disaster, They knew about that O-ring problem. That was a critical design flaw, and they ignored the warnings. And then the loss of 7 lives, including a civilian, Krista McAuliffe, the public impact of that, it
Yeah.
was huge. And it really exposed those deep organizational issues at NASA.
Yeah, Challenger, it really shook people to the core.
It did. And while Columbia, that foam strike wasn't as directly linked to a known problem, it still revealed similar organizational issues at NASA. And of course, those Soyuz missions, they highlighted critical system failures, even though the death tolls were lower.
And let's not forget the human cost. Every single one of these events, it represents a profound loss.
So taking all of that into account, the scale of the failure, the impact it had, the lessons we learned, I think it's fair to say that the Space Shuttle Challenger disaster, it's widely considered the biggest engineering disaster in space. The fact that they knew about that O-ring problem and still launched, that's what makes it so significant. It was a systemic failure, a failure to heed those clear warnings.
And that's a crucial lesson, right? That we can't let deadlines or pressure or anything else compromise safety. These disasters, as tragic as they were, they've taught us some invaluable lessons about design, about testing, about communication, and above all, about the importance of a strong safety culture.
Absolutely. They've shaped how we approach spaceflight today. They're the reason we have those redundant systems, the fire-resistant materials, the escape procedures, the rigorous testing. We owe it to those who are lost to never forget those lessons.
And as we keep pushing further, exploring Mars, going beyond, we've got to remember that space, it's unforgiving. There are always going to be new challenges, new risks. The question is, can we learn from the past? Can we ensure that our ambition, our drive to explore, never overshadows the absolute necessity of safety?
It's a question we have to keep asking ourselves every step of the way.
Yeah, every single step.
So folks, there you have it, a look at some of the most significant engineering disasters in space history. And as we move forward, let's remember those lessons. Let's honor those who were lost by making space exploration as safe as we possibly can.